Okay, I think we can get started. So I usually like to start this class off with introductions, obviously with a number of people and with the fact that we're not in the same room. We're not going to be able to introduce ourselves in person, but if in the chat section, you could just write what your name is, if you are primarily at UCLA, and what your research is, or what your laboratory, what your research and laboratory are, or if you're not in a research laboratory, what kind of work you're planning on doing with Python. It gives a good opportunity for people to meet each other. Obviously, it's not mandatory, and if you don't feel comfortable doing that, feel free not to. But it is a good opportunity to meet people who might be working on the same thing and can help you along. All right, and who's watching some kind of sports over there? Because I can hear your microphone. Oh, I guess I know who it was because he just muted himself. Oh, and hi, Khadija. Good to see you again. All right, so while everyone is putting in their information, I'll just give mine really quickly. So most of my experience is actually on the molecular and animal modeling side. I have about 5 years sort of programming and informatics area, which was also shared with the molecular side. Before that, for about 15 years, I was purely bench science, doing a lot of mouse modeling and that kind of thing. That said, I got into programming pretty hard, so I find that my background at the bench gives me a much better understanding of what I'm doing. In terms of biomedical research experience, I've done a lot of work in metabolism and developmental bio, as well as genetics. On the informatics side, I've done a little bit more stuff with CRISPR design, cancer immunology. And actually what I'm primarily in right now is I do a lot with microbiome analysis. So if you are doing work with metagenomics or microbiome, I'd love to talk. And actually right now I've been retasked from microbiome to designing some tools to help with analyzing test results from coronavirus testing. Oh, and hi, Christine. Okay, so going back to this, I also do some work with data security as well. So at some points in the class, I'll also help you understand a little bit about how some program flaws cause data to be leaked or cause computers to be taken over, that kind of thing. So the class structure. As a general rule for me, the ending time is more of a suggestion than a rule. In fact, usually this class, we will probably be ending earlier rather than later. So I think the class is scheduled to run until about 4:30, but generally, just about every day you should expect to be getting out before 4 o'clock. Obviously, it depends on the questions I get. The other thing is, because I have to help people understand what's going on sometimes when stuff's not working, I may ask people to share their screens. If you're able to, obviously that's quite helpful. So for example, if you have code that's not working, or if something else isn't working quite right, or if you want me to see a piece of code, I will need you to share the screen, so you'll presumably be sharing it with a class. I say that because just so you're ready to share your screen, it's important to make sure that, for example, you don't have anything up on your screen that you wouldn't want on the front page of the New York Times with your face looking at it. A friend of mine teaching a class already had an issue with that, where a student shared a screen and they had browser tabs that they probably didn't want to share with the rest of the world, and I'll leave it at that. So topics that we're going to go over. A lot of what we're going to go over today is just an idea of data structures. So I think one of the things that is quite helpful is just about everybody in this class is some kind of a researcher. And the cool thing about being a researcher going into programming rather than a programmer trying to help with research is we understand our data and our data structures better than a lot of other people. We know the rules, we know the exceptions. We generally know the best way to move around our data. And it turns out that by knowing how the data should be structured and how it should interact, you're typically going to be able to come up with better programs and better ways of analysis than somebody who just understands how to write code. So first I'm going to talk about unstructured or minimally structured data. So in the beginning, there was a Boolean, also known as a bit. And a Boolean is really just something that can be 1 or 0, true or false, a yes or no, alive or dead, positive or negative. Something that can exist in one of two states with no overlap. So these are the basic unit of computer information. And in this case, actually, all the computer knows is sort of on or off. So your computer's memory is just a bunch of very, very tiny atomic scale switches. And the switches can either be set to on or off. And the state of the switch is what your computer uses to basically call a 1 or a 0. But if you start stringing these together, or you start doing operations on these, you can already start to do some computing. So there's something called Boolean logic or Boolean algebra. And for example, taking a true and false will come out to false because with an and statement, both sides have to be true or else it comes out to false. For an or statement, only one side has to be true, or in other words, both sides have to be false for it to be false. That's a little bit different than the or most people use in their daily language, where you typically mean the first side or the second side, but not both sides. That is actually called the XOR or the exclusive OR. And that's where you're saying the first thing can be true or the second thing can be true, but they can't both be true and they can't both be false. Or in other words, what XOR is really saying is one thing has to be true and one thing has to be false for it to be true. If they're both the same, it comes out to false. And then finally, there's not, which just flips around the value. So not true comes out to false, not false comes out to true. So this is the most atomic unit of digital information. And in fact, this is kind of the most atomic unit of information there is, just a yes or a no, a true or a false. Unfortunately, because of this, it's also kind of boring and you're somewhat limited in what you can do with it. So what can you do with Booleans? You can classify things into strong versus weak bases, classify purines versus primitives, true versus false, a whole bunch of these other options. You can string them together, and if you've seen what a FASTQ file looks like, or actually not a FASTQ file, but a SAM file, the SAM file has something called flag values, and these flag values are represented by an integer, but what they really represent is a collection of true-false values describing a sequence alignment. And you'll learn at length how to deal with those in a bit, because you'll see how those are kind of read. So simple sets of Booleans can represent integers. You basically string together a bunch of Booleans, and you have a number that's in binary. So anything you can represent with a whole number, you can represent with a Boolean. Lengths that are measured in whole units, numbered indices, rounded values, counts, base positions, that kind of thing. So anything where you represent it with a whole number, you can do with a Boolean, with a set of Booleans strung together to form a binary integer. You can also represent anything you need to increment, so counters or positions. And the cool thing about integers is it's pretty easy to understand how they're strung together. The first bit is equal to 1, the second bit is equal to 2, the third bit is equal to 4, the fourth bit is equal to 8, which is a lot like our numbering system where the first number is equal to something times 1, the second number is equal to something times 10, the third number is equal to something times 100, the fourth number is equal to something times 1,000, and so on. So another example of this is using an integer to represent a collection of Boolean values. So this is a line from a SAM file. A SAM file line just describes the alignment of a DNA sequence against a reference. So here we see a SAM flag value of 99. What does a flag value of 99 mean? So flag value tells you about its mapping properties. And again, these are a bunch of things that can either be true or false. The read can either be paired or unpaired. The read can either be mapped in a proper pair or not mapped in a proper pair. The read can be either mapped or not mapped. The read can either be the first in the pair or not the first in the pair, and so on and so on. So for example, a flag value is 66. So that would be 64 and then 2. And that would be saying that the read is the first in pair and the read is mapped in a proper pair. And I should point out some flag values can't really exist. So a flag value of 66 can't actually exist. And the reason for this is if your read is first in pair and your read is mapped in a proper pair, your read is also paired. So this would actually mean that you couldn't have a 66, but you can have a 67. There's a program online that'll help you explain these things. And again, Booleans are things you can represent just with a checkbox. And if you look down here, you'll actually see the digits that make up both a flag value and a binary integer, where the first digit is equivalent to 1, second digit is 2, and so on, all the way out here. And if you wonder why computers seem to like numbers like 1024, despite the fact that it seems like a very odd number to show up, or 512, or 256, it's because these are numbers that are perfect, that are squares of 2. Or that are powers of 2. So again, to get a number in binary back to decimal and vice versa, the way we're doing it is it's just this number times this number, and then sum them together. Now, obviously, integers don't work for everything. Sometimes you need real rational numbers. So essentially with an integer, it's very easy to represent in binary because with an integer, really, we know what our precision is. It's a single unit. And we know what, and really the only thing we have to agree on for convention is the first digit the most significant or is the first digit the least significant? For floating point numbers, that's a little bit more tricky because they're, you have a rational and you have to start worrying about things like precision levels and that sort of thing. So structured data, this is where we start getting into more complex things where we have data organized. So we're typically going to take some of these very simple values like for example, Booleans, integers, or single characters, or floating point numbers. And we're going to start putting them into a matrix or an array or a list of values or whatever you want to call it. So these indexed sets of data, they can be heterogeneous or homogeneous, and it depends a lot on the language. So for example, in Python language, you can have a list, and Python natively has lists as what it stores data as. And the first element of the list can be an integer, and the second element of the list can be a word, and the third element of the list can be a Boolean. Contrast that to a language like C++, where you have arrays, and in an array, the first element can only be the same thing as all the other elements. If you take a two-dimensional list or a two-dimensional array, you get a matrix, and that's how you deal with different dimensional matrices. So depending on the storage method, these can be very efficient to process through a process called prefetching, and I'll go into that a little bit later. But depending on how these are stored, you can actually access them from memory with super high efficiency. These are always going to be indexed. So the way you get a specific value out is you say, I want value 0, I want value 1, I want value 2, and so on. So these are all indexed to 0, which means the first value is going to be index of 0. And these are useful for things that come in series. So for example, a series of letters makes a word, or a series of letters makes a sentence, and that's how you work with this. A series of numbers can make, for example, a time series. So if you're following the value of a stock, and you're taking its value every day or even every hour, you can just build this up into a list. A series of symbols, you can do that. There's various things you can do with that. If you take a list of lists, you form essentially two-dimensional matrix. So Python is very strict about reading and writing out of bounds of your matrix. And this is really important because if I make a 10-element list and I ask for the 11th element of a 10-element list, Python will actually throw an error back at me saying I've read outside the bounds of my list and I made a mistake. Another example of this would be a language like C++, where if I have a 10-element list and I ask for the 100th element, it's going to go in the computer's memory where it assumes the 100th element would be, regardless of the fact that there's not actually a list element there. And it's going to try and read that back to me. And that's just going to give me back something from memory that I shouldn't be accessing. This is one way that a lot of times computer malware works, or a lot of times sensitive data is disclosed, is somebody tricks the computer into reading things beyond the bounds of the variable that it should be reading or beyond the end of a string. And speaking of strings, if you take a series of characters, this forms a special kind of list called a string. So for computers, a string is just a set of characters or an array of ordered characters. And again, you can index it by number. So you can pull out, for example, the second element, which will be, for example, in this string down here. So in computers, strings are almost always denoted by being surrounded by either single or double quotes. So if I pull out the second element of this, it'll be a 1. You have a little bit more functionality if you treat a string of characters as specifically a string rather than just a list, because strings are restricted to what kind of data they can hold. It's just an array of characters. It's a one-dimensional array of characters. Python will not implicitly treat string 11 as number 11. And this is important to note because a lot of other languages will try and do their best guess as to what you want to do with it. So for example, Perl and C++, if I take string 11 and try and add number 12 to it, it's going to come back with number 23. Python, on the other hand, is a little bit different. What Python wants to do is if I take string 11 and string 11, it's going to give me back string 1111. If I combine integer 11 and integer 11, I get 22. If I combine string 11 and integer 11, I get a type error saying I can't add basically a string and an integer together. If I force number 11 to be a string, that's perfectly fine. I can still do that. But again, other languages may try and do a lot of implicit conversion. Python does not want to do that. All right, and then the last major kind I'm going to talk about here are key values. So key value is where you can look something up by the key and get back its value. And this allows the recall of some data by looking up its key. So essentially in Python, it's called a dictionary. In other programming languages, it's called a hash table. The keys have to be what's called unique and immutable in Python. And what that means is you can't have something like a list or another dictionary because you can add or remove values from those. You need something that's a fixed value. So an integer is perfect, a string is perfect, a tuple is perfect because that's actually a set of fixed values, but you can't use another dictionary and you can't use a list. the value can be anything. So the value can be another set of key values, so you can make multiple level dictionaries this way. In a dictionary, if you enter a new value for a given key, that'll replace the existing key, or that'll replace the existing value for that key. If you enter a new key, then it'll just create a new value in the dictionary. Dictionaries have no inherent orders, although Python, I think, does try and return dictionary keys to you alphabetized or whatever, or in some kind of an order. The keys have to be unique. So a dictionary can't have a repeated key, and you can use that sometimes to force values to be unique. Some languages like C++ and Perl don't remember your set of keys. So you have to actually be the one who has something in there to remember what all your different keys are. Python, however, does maintain a list of keys, so that's not a big issue in Python. And you can actually build some very nice hierarchical structures using these dictionaries. So you can already imagine that you can build a dictionary of subject to their result, or a gene to its mRNA length. Or you can build a dictionary of species, and for each species you have a dictionary of genes, and for each gene you have a dictionary of mRNAs. And for each sequence, or for each mRNA, you have its sequence. So just as an example, I would look up Homo sapiens. You know, I look up sequence dictionary, Homo sapiens, TRPV4, mRNA sequence number 1, and it would return to me the mRNA sequence for TRPV4 mRNA sequence number 1. All right, objects, and so we'll get into objects and object-oriented programming, and then we can actually start doing stuff. So hopefully the stuff I went over previously was reviewed for people. Is there anybody who feels like they're not confident in understanding some of the basic data structures? Even if you don't understand how to implement them in Python yet, just kind of understanding the idea of integers, lists, dictionaries, floating point, that kind of thing. If there's anybody who has questions on it, I'll give a minute or two for people to ask questions in the chat window, and then I'll go on to object-oriented programming. All right, I'm not seeing any questions pop up. All right, so what are objects and what is object-oriented programming? So objects are a combination of functions and data. And it's basically for building up these structures of data and functions. So when you have a function associated with an object, it's called a method. And when you have data associated with an object, it's called attribute. So just as an example, I drive a Honda Civic. My friend Casey drives a really massively oversized Jeep. They're both fundamentally cars. So they could both be considered instances of the car object or of the car class. However, they're also very different in some ways. So if I look at the engine attribute, his engine is going to be very different from my engine. If I look at the tire attribute, he likes to go off-roading on the weekends. So his tires are going to be very different from my tires. And truth be told, the tires may be their own object, and the tires are going to have their own set of attributes. So his tires are probably going to have a higher cost than my tires. His tires are also going to have much deeper tread than my tires. And since he likes going off-roading, his dirt attribute is going to be much dirtier than my car's dirt attribute, probably. So a class is a type of object. An object is an instance of its class. And again, you can have two different genes, and genes are going to have some of the same properties, even if they differ in how those properties show up. But they're still going to have some universal attributes between them. They're both going to have some location in the genome. Even if it's a different location, they'll both have a location in the genome. They're both going to have a function that can be ascribed to them, or maybe an unknown function. They're both going to have probably a %GC content over the length of the gene. They're both going to have mRNAs that are made, and so on and so on. So those are attributes. I can also think of them as having different methods. So for example, if I was a cell and I have a gene object, I want to express it, there's basically express functionality. Sorry, my PowerPoint just decided to go off. There we go. So in Python, it's a good, and in most programming languages, it's a good convention that when you refer to something that's a class, it starts with a capital letter, and when it's an instance, it starts with a lowercase letter. Get in the habit of doing this. I'm not very strict on a lot of the style rules, but this is actually a very good rule to be strict with. It avoids a lot of confusion later on. So in Python, it turns out just about everything you're doing is an object. And in Python, you've probably noticed that a few times already, when you've called, for example, some variable or some object, you call it with object.method, and it'll have opening and closing parentheses after it. Even if you don't put any arguments, it'll still have them. If you call an attribute, which is just returning to you a piece of what should generally be static data, then you're just calling object.attribute. There's no parentheses after it. So an example of the class, so I think you all have the raise hand button. So quick show of hands, who out there knows Rick and Morty already? All right, I'm seeing quite a few hands going up. Okay, so from Rick and Morty, some of you are probably already familiar with this guy. His name is Meeseeks. And he basically exists with one purpose in life, and that's doing some very simple task that's very well defined, should take only a small amount of time, isn't too complex. And then he goes out of existence. And apparently he doesn't like existing very long, but that's not super relevant to us right now. But anyway, so he exists to do just one thing, and then he goes away. So Meeseeks is a class. Here we see two instances of the Meeseeks class, and we can see they have some common features, but they also have some differences between them. So this, for example, is stupid hat Meeseeks, and he has a stupid hat on. This is Meeseeks with a stupid haircut, so he has just a little tuft of hair. He has no hat. And I got a ding here. I'm not sure exactly why. Oh, now I know why. All right, so in Python, pretty much every piece of data you've ever worked with, even if you didn't realize it, is an object. So in Python, all your lists, all your strings, and just about everything else are actually objects, it turns out. And as you know, and a lot of these objects have different methods attached to them. So you started off, for example, in Python learning about lists. And you may have even seen that you can do list.sort, and that's because list is an object and sort is a method associated with lists. You also have remove, and that'll tell it to find in this list G and remove it. So if I do list.remove G, I have a list now without a G. I can also tell it to delete an element, so I can delete list element number 3, and that gets rid of this one right here. There's also pop, and pop is an interesting function. Pop will return some element from the list, in this case, element number 1. So remember, the first element of the list is always a 0. So pop1 will delete this and then return it. And this is the general structure of creating a class. So I'm just going to walk through this really quickly. So we have class called, in this case, my class. Objects are going to start off with initializers or creators. And the way the creators work is you're going to start off with at least self. And self is an interesting one. I don't expect everybody to get it right now, but it's essentially referring to this instance of the object. And it's going to take in a couple of values in this case. So it's going to take in some required data and some optional data. And in Python, optional data, you can tell an argument is optional because it'll have a default value set for it. So here I'm taking in the my required data value, setting it to self.required data. So this is actually making this is making this value that was passed in into an attribute of the object. My optional data, this is making it an attribute of the object as well. Objects are also going to have methods, and these are functions attached to the object. So I can do combine data. So here I've defined a method. And what combine data is going to do is it's just going to say if there's optional data, it's going to add them together. Otherwise, it's going to return just the required data. And the last one is a method that starts and ends with double underscores, which in Python, a lot of people just shorten down to dunder. And typically, if you see a method that starts and ends with double underscores or if you see a dunder method, that's because it's a special method that is considered an overload. So for example, this init is kind of a special method for the object. This string method here is saying that if somebody tries to call the object as a string, so for example, they try and print the object, what they actually want is, in this case, combine data. And then here you can see how I interact with it. So test1, so I'm just instantiating my class up here to test1, which means that test1 is now an instance of my class. If I do test1.combine data, it's just going to return something because something is all I gave it. I only gave it one value. If I call it as a string, it'll return, again, that value. Test2 is another instance of my class, in this case with two things in it, so thing1 and thing2. If I do combine data, in this case, now I combine them together. If I do a string, I again just call that combine function and get the value for it. I can also call the attributes directly, test1.optional data, test1.required data. So test1.optional data, it doesn't really have anything. Test1.required data, it does. And if I call test1.myOptionalData, which, as you'll notice, my optional data exists here, but it isn't actually made into an attribute of the object. What you'll see is that there is no attribute of that name. And the reason I bring this up is most people in this class, is people who deal with a lot of scientific data, you actually have a better start than a lot of programmers trying to do the same thing that you're doing, whatever it happens to be. So somebody kind of famous was quoted as saying that he's a huge proponent of designing your code around the data, which means the better you understand the data, the better you're likely to be able to code, at least once you kind of understand how to code. He was also quoted as saying the difference between a bad programmer and a good one is whether or not they consider the code more important than their data structures or vice versa. And that bad programmers tend to worry more about their code, and good programmers tend to worry more about their data structure and their data structure relationships. The person who said this is Linus Torvalds. He's the guy who wrote the Linux kernel. So he basically invented Linux. So definitely somebody who knows what he's talking about when it comes to computer practices. Also, it was difficult to find a quote of his that didn't have profanity in it because he likes to swear publicly and really awkwardly. All right, so as a general rule, I'm trying to keep with the UCLA standard of anything running an hour or more, I should include breaks. So it's 2:15 now. This is probably a good opportunity for a quick bio break. So go stretch, go get some water. I guess I don't have to say restrooms are behind the elevator because I don't think any of us should be in Boyer Hall right now. But everybody's welcome to take a quick break. And let's see, it's 2:15, so let's get back together at 2:25. And we'll pick up again, and we can start actually working with some code now that I've gotten through all the introductory stuff. Feel free to interrupt with questions. you can pop them up in the chat, or if you have something that, or you can also feel free to unmute yourself and ask the question if you have one. But other than that, I'll come back in a moment myself and answer any questions. Otherwise, I'm just going to go refill up my water for a minute. All right, we'll pick up again in about 3 more minutes. And I see that somebody had a question, so as soon as we resume, I will pick it up. All right, it's 2:25, so I think I can pick this up again. All right, so first question. Could I explain again what it means for a function to be overloaded? Yeah, so function overloading, pretty much everything in Python, and this might actually be better if I do it live. All right, so everybody should be looking at my command prompt. Can somebody really quickly in chat just confirm that you're seeing my command prompt? Awesome. All right, so I'm going to kick off Python. And I'm actually going to define a class here. So all right, so I just did a very basic class definition. And what's interesting is if I do so there I've just defined a very basic class. And the variable is 1. Now if I call another variable in here, it doesn't exist, so I get an error. If I try and call it up as a string though, so I'll force it to be cast to a string, I get back this thing, which basically says that it's something in main, it's my class object at some memory value. This is not super informative. So I'm going to do the same thing as before. So I'm defining a new class. And I'm having it return, in this case, just a string overloaded. So here you see that I've defined my new class as test2. So if I call test as a string by trying to print it, I get that. If I call test2 as a string, it says overloaded. So the question is, what am I overloading? It turns out that every object in Python starts off with a way of showing it as a string. And that way of showing it as a string gives you this type of thing, where it just says where it is, what it is, and where it's stored in the computer's memory. If I want to make something a little bit more useful, I can overload string by using this dunder method string. And in this case, I just have it return overloaded. I could also have it return the string value of variable or whatever else I wanted. So for Kathy Lawrence, does that make sense and answer your question? Okay, awesome. All right, I also have a question. What is the self in definition in def in itself? What does that mean? Self is actually one of the more complicated things to understand in object-oriented programming. Self refers to that instance of the class. Pretty much for now, you can just about always assume that you're going to have self as the first variable in any method related to an object. And later on, you'll start understanding the super rare instances where you don't use it. I think myself, I've only ever written 2 or 3 methods that don't that didn't actually use self. And they didn't use self because the object hadn't been created yet, it was being created. But pretty much other than that, you're pretty much always going to use self. And what self does is it gives you access to that instance's attributes and functions. So does that make sense? Okay, perfect. Yeah, self is one of the more complicated things to understand really easily. All right, so I'm going back to this where we're going to have a look at our SAM file. So again, a SAM file. Quick show of hands for just use the raise hand button. Who out there deals a fair amount with sequencing data from like Illumina or anything like that? Okay, and I see a few names on the list who are also in my morning class. So if you're in my morning class, you're going to get really sick of this file format very quickly. But this is called a SAM file. So I showed you before, this flag value has meaning in terms of some binary values. One of the key things in the SAM file is also the DNA sequence it detected, but it's telling you it detected what the DNA sequence was that was read and where the aligner thinks it came from in the genome. So I think for most of the audience, this should look pretty familiar. It's a long string of A's, T's, G's, and C's. So it's a DNA sequence. And let's think about the DNA sequence as an object, because basically a DNA sequence is data. So what are the attributes of a DNA sequence? There's going to be the sequence itself, and again, that's going to be a long string of A's, T's, G's, and C's. It's also going to have length. It's going to have some percentage of A's, T's, G's, and C's. It's going to have a GC content. And for people who deal with DNA, especially on a molecular level, the GC content tends to be very important for understanding some of the physical and chemical properties of the DNA sequence. It's also going to have a reverse complement. There's also going to be some methods you can do. So for example, getting subsequences or looking for restriction site sequences, promoters or translation start sites. You can also, and this has to be a method, look for matches and mismatch counts and positions. So a couple things to think about with attributes. Typically, attributes are going to be things where you don't have to get any outside arguments. So the sequence itself, presumably once you have your DNA sequence set and you create an object around it, you're not going to change it. If you need a different DNA sequence, you just make a new instance of DNA sequence class. Since the sequence itself won't change, the length is going to be fixed. So that's something else that you can pretty much keep static. You really don't need to recalculate the length of your DNA sequence every time somebody calls it. And in fact, that's computationally kind of wasteful. Since the sequence itself, the way we're building this is we're assuming that a sequence itself isn't going to change. The percentages or base composition is also not really going to change. So that's something that you could write a method that just calculates it and then just stores it. Since the sequence doesn't change, the GC content doesn't change. And since the sequence doesn't change, the reverse complement doesn't change. And do people out there know what a reverse complement is? Or is there anybody who wants me to explain what a reverse complement is really quickly? All right, anybody who isn't familiar with the idea of a reverse complement for DNA, just hit the hand raise button. I'll know if I need to explain it. Okay, I'm getting a few people who are a little bit unfamiliar. Okay, so I'm going to assume that most people here remember at least a little bit of biology, and you remember that DNA is double-stranded. And I'm also going to remind you that with DNA, A always pairs with T, and G always pairs with C. So the two DNA strands that are paired together run in opposite directions. And for example, if I have a sequence that in one direction is like this one, ATGC, then going the other direction, I'll have a sequence that goes GCAT. And that sequence that is reversed and complementary to the first sequence is the reverse complement. So for people who are unfamiliar with reverse complement, does that make a little bit more sense? Okay, I'm not seeing any more questions, so I think that should work. But basically, it's figuring out the DNA sequence that should bind to and pair with this other DNA sequence. For these methods, these are going to be things that are likely to need additional information. So for example, if I want to look for restriction sites in the DNA sequence, so these are just sites where the DNA can be cut by a known enzyme that cuts a known sequence, I would need to supply it externally with what the restriction sites are. If I want to find promoters, I have to give it the definition of a promoter. If I want to find translation start sites, I probably need to tell it what a translation start site is going to look like, although probably ATG. For doing match and mismatch counts, in order to compare and contrast two DNA sequences, I would need the other DNA sequence. So that one definitely needs to take an argument. Okay, so going back to the SAM file, what are the values we have in a given line on the SAM file? So we can start thinking of the SAM line as basically being a class, and the SAM line holds data from a line in a SAM file. And these are different attributes we can have. So we can have samline.readID, because this first field is actually just the identifier of the read. Samline.flag, and that's just the flag score. Samline.chromosome. Samline.read start position. And if you look at some of these, you can even start figuring out what they are. Like the read start position is a chromosomal position. That's pretty much always going to be an integer. Chromosome, that's going to probably be a string. Flag value, that's going to be an integer. Read ID, that's got to be a string. Read alignment Fred score, that's always going to be an integer. Cigar string, that's going to always be a string because that's letters and numbers. So the mate chromosome, that's going to have to be a string as well, because we're either going to store the equal, or more likely we're going to want to store the chromosome 14 value. We also have the mate starting position, that's going to be an integer. We have the read length, that's going to be an integer. DNA sequence. And we're actually going to have this be a custom object we build called a sequence. So samline.sequence. And we can build an object for handling DNA sequence specifically, because maybe we want to do some more work on that. So what's cool is an object can actually contain other objects that we make. We have our quality string. And we'll see in a little bit that we can actually write the quality string into an object that'll convert that. We also have a bunch of these tags afterwards that for the purpose of this class, we're not going to worry about too much. So when we think about it, how many of these attributes should be classes themselves? We already talked about DNA sequence as an object. Flag score could be a class that does analysis on the flag score. That's a definite possibility. The quality score could be translated to actual numbers. That would definitely be useful. And maybe some others. All right, so the first thing we're going to do is we're going to either create a new file, or you downloaded the data, so you should have this file already, is Python class 2/DNA sequence handler. The folders the folders and file names tend to be case sensitive, so make sure that you're careful about how you capitalize and lowercase things. And I don't know, where do you download the data from for this file? I have a question coming in. So were you able to get the link to Google Drive that I sent out earlier? Okay, I just posted the link to the Google Drive again. So if you follow that link, that should take you to where you can download the course material from. And I'll give you a minute or two to get that. But from the previous class, we have our reverse complement generator. So I'll go over how this works really quickly. Can somebody tell me, are you able to see my mouse pointer on here? I think usually it shows up, but I just want to make sure because some people were saying that it's hard to see. Okay, so everyone can see the mouse pointer, perfect. Okay, so here we've defined a function, and that function we've defined is reverse complement. And the truth of the matter is, I'm going to give people actually a lot of time to just play with code, because I don't think anybody can teach. Oh, and I have a question about what last class. So did people here take the Python 1 class, or the original Python, the intro to Python class? Okay. So if you took, actually that's a good point. The intro to Python class, when I made this class, one of the things they taught was writing a function to make a reverse complement for DNA. And it was actually one of the, it's one of the last things people would do in the class. So I tended to like starting with it for code. I haven't actually sat through the newest Python course, but I know it's changed around. So I actually don't know for sure whether or not they still have that. But either way, I'll actually walk through this one, so it shouldn't be, okay, so you did go through that, perfect. Okay, no, so somebody's mentioned, yes, I do have a morning class. The morning class is actually going through Intro to NGS. So when I say last class, I'm referring to the previous Python class, not, somebody's asking if you can use Spider for this practice. Yes, you can use anything you want for this practice. Okay, and somebody else is saying that you did reverse complement, but you didn't use a table. Yeah, that's fine. I do the reverse complement through a slightly different method just because I want to show there's more ways than one to do it. And also there's sometimes ways that are slightly more elegant than other ways. And there's a few Python tricks that I wanted to introduce as I show you this. So it does the same thing, it just does it slightly differently. Anyway, what I was going to say before is I can't, with just a few hours of lecture, I can't turn people into programmers. So really the trick here is I'm giving you a lot of code that you can play with and some data that you can play with. And the goal is that you be able to mess around with it yourself. Really what I like to talk about in this class, and the main thing you should walk away from here with, is if you have an idea for a program, or if you start asking yourself, I wonder if I could write a program to do something, the idea of this class is this is going to hopefully give you some ideas about how to attack writing a program. And that's something I always personally, these are the two things I always kind of felt personally were missing from teaching programming to people who are more maybe a background at the bench. Number one is teaching programming from the understanding that this is somebody who already has a very good understanding of the data they're likely to be working with. And number two, how to actually approach writing a computer program rather than just teaching people how to write hello world or that kind of thing. how to approach starting off with a problem and coding up a solution. So going back to what I referred to as last class, the challenge here is just to write a function that creates a DNA reverse complement. So the first thing I define here is a complement table, which is just a dictionary. And it just says which bases are complementary to which other bases. So A to T, C to G, G to C, T to A, and then N to N, because N actually means unknown base or any base. So any base can be complementary to any base. I'm introducing a pattern here. So I have reverse complement or rev comp equals, and then open and close quotes. So somebody in chat tell me, what does it mean when I have just open and close quotes with nothing in between them? Yes, empty string. And you're going to see this pattern in this class probably 50 different times. So this is usually what's called initializing. I'm initializing an empty string. And something that, again, you're going to see me do a lot in this class is I'm going to start off an operation by initializing an empty string or an empty list or an empty dictionary. And then you're immediately after it going to see a loop. And this is kind of introducing one of the first programming patterns that a lot of people are get into, which is initialize an empty value and then run a loop to add stuff to it. So here I'm saying for base in DNA sequence. So the DNA sequence is presumably going to be a string of A's, T's, G's, and C's, and maybe some N's. And saying for base in DNA sequence is essentially saying iterate over the DNA sequence. And does anybody know what this thing is at the end, where I have open brackets and then 2 colons and then a -1 and then close brackets? Anybody know what that's called in Python? Cool. So at least one person knows it is called slicing. Has anybody seen this structure before where I have colon, colon, where I have colon, colon, the value? Yes. Going backwards one step. So in Python, slicing is taking a portion of some kind of an index value, so either a list or a string. The first value is a starting position. The second value is the ending position, non-inclusive. So for example, if I start at position 0, I'm starting at the beginning. If I go out to, say, this value being 5, I'll take everything up to but not including index value of 5. And this last value, which is one of the least frequently used, is the step. So a step of 1 is the default, and that's just take each element in order. A step of -1 says start from the end and work back 1 index at a time. So what I'm actually saying here is, since I did set these 2 first values, go over the DNA sequence base by base, and just each time here it's going to analyze the base. Start at the very beginning, since I didn't give anything else. Go to the very end, again, since I didn't give anything else. But do it backwards, 1 value at a time. So it's going to start at the last letter in the DNA sequence and go back 1 letter at a time. And here all it's doing is saying reverse complement plus equals. So it's saying add to the reverse complement table, add to the reverse complement, and then look up the reverse complement base in the reverse complement table. And once it's done with all this, it'll return the reverse complement sequence. Does that kind of make sense to people? Okay, is there anybody who feels like there's something in here that needs further explanation? I'll give a minute or 2 for people to submit questions. Okay, I'm seeing a couple yeses. I'm not seeing any questions pop up. Oh. No, DNA sequence here is actually a string. Okay, so DNA sequence is being passed as a string because, like I said before, you can actually think of a string as a list of characters. So iterating over a string is just like iterating over a list of characters or iterating over any other list. Okay, so the plus equals. The plus equals is an operator that says add to the currently existing value. So for example, so revcomp plus equals means take the existing revcomp and add this value to it. And somebody's asking about the lookup. So the lookup is actually just saying, take the base, look it up in the complement table. So for example, if the base is an A, it'll return a T. So this will evaluate to a T. And then it'll say revcomp plus equals T. So if I start off with an empty string, then now revcomp is going to become T. If the next value, so if the DNA sequence that came in was AC, then the first iteration here, since I'm starting from the end, I'll start with C. I'll look up, this will tell me to look up C in here, and it'll be G. So revcomp plus equals G. Since revcomp is empty, will just give me back a G. And if the first letter was an A, for example, then I go from the second letter to the first letter, which would look up A and add a T. So it would be, so I'd wind up with GT. So the plus equal is essentially just telling it add to the existing value there. All right, I have a question. Can I explain how the table interfaces with a code so efficiently? So this table is just a dictionary. And the cool thing with a dictionary is when you look up a value in a dictionary, the dictionary will return back the value. So in a dictionary, you have what are called keys and values. So the dictionary keys here are this column of letters. The dictionary values are this column of letters. So the dictionary keys, again, have to be unique, and they have to be sort of closed form. So for example, a letter is a perfectly closed form thing. So if I tell it complement table of A, it'll look up A and return a T. And then somebody asked about why I go backwards. And yes, the exact reason why I go backwards is because by convention, DNA is read 5 to 3. So make sure that I keep things going in the same direction. So I think in the first Python class, you iteratively add bases to the beginning of the string you're building, but in this one, I just read the sequence in backwards. Oh, they don't go over dictionaries in the first Python class anymore? Oh, okay. Yeah, dictionaries are what I consider they're like a fundamental data structure in Python. So definitely good to learn dictionaries. They're, for me at least, they're some of the most, it's like one of the most versatile basic data structures that I deal with. Okay, I didn't realize they weren't going over dictionaries still. They weren't still, that you didn't go over dictionaries. Okay, so I'm glad I went over that in detail then, because dictionaries are super, super important to understand. Okay, and I have a question, how does the N work? So N is a placeholder for when you don't know what base is there. Or alternatively, N can mean it's any base. So any base, I can't say what I can't say what any base complements with beyond the fact that it could be any other base. And yes, N sort of stands for no call, but really N is actually like, N is like officially recognized by IUPAC or whoever else the governing bodies are as like the official stand-in for any DNA base in the degenerate code. And I have a question: if you shouldn't look for N in the code as a letter. In general, you shouldn't be looking for N. You shouldn't be searching DNA for Ns unless you want to specifically look for regions that are not completely sequenced or poorly sequenced. If you have a region with a lot of Ns, then the main piece of information you get out of it is that it is that region is not well understood or well sequenced. Oh, you're saying, does that mean we shouldn't look for N in the code as a letter? No, you can assume that you might want to assume that N can come in as a letter. There's actually, I actually have a different version of this dictionary that has a lot more, that actually has a lot more values in it. So I used to have it memorized. I don't have it memorized anymore, but there's actually an official table of single letters that represent each possible combination of DNA letters. So N just represents possibly A, possibly T, possibly G, possibly C. But for example, the letter S would represent G and C, the strong binding bases. And letter W represents A and T, which are the weak binding bases. And so, for example, S always pairs with S, and W always pairs with W. Yes, there's a pre-existing logic this dictionary was built off of. There's actually also there's a convention of which letters represent what in sort of the degenerate DNA code. And there's also even a standard, and I'll get into this later, for which colors should represent which base. There's actually a chemistry and biochemistry governing body that basically said that that A should be represented by blue, T should be represented by yellow, G should be represented by green, and C should be represented by red. Like that is an officially documented color code for DNA that we'll get into actually tomorrow. So what would happen if the sequence had a J in it? And I think J is actually one of the letters that's not even in the official degenerate code. So what you would get is you would actually get a key error. If you try and look up a key in a dictionary, but that key doesn't exist, so in this case, for example, I look up J in this dictionary, which clearly isn't there, it would actually throw an exception in Python. And that's something I can talk about a little bit as well. I'm going to switch my share for a moment. All right, so I'm going to switch to this. All right, and thank you, Garrett, for sending the IUPAC codes. And like I said, even less known is there's actually officially IUPAC colors for each base. All right, so I just defined a very basic dictionary here where 1 keys to A and 2 keys to B. So if I call up my dict value 1, it'll return A. If I call up mydict value 2, it'll return B. Note that I can't go the reverse direction because B doesn't exist as a key. And if I call up something that really doesn't exist in there, for example, J, it'll return a key error of there's no key in there called J. There's actually programming tricks to deal with this. So it's called the try except. I don't typically cover in this class, but I figure I can go over it for a moment here. So it's going to here try looking up mydict of J, although it won't do that till I finish this block. So in this case, I have a, yeah, okay, so you went over try except blocks. Wow, you went over try except blocks, but not dictionaries, okay. So anyway, try except is if you expect a certain error, this will actually tell the program how to gracefully handle the error. So in this case, it just prints invalid key given. So I'll switch back now to my regular share. So yeah, so to go back to your question, how I would deal with people submitting, for example, a DNA sequence with a J in it, I would probably build in a try except block where it would try to look up the base. And if the base given was, for example, a J, it would probably still crash out the program, because if somebody's submitting a DNA sequence with a J in it, they need to go back and check that out. So it would probably crash out the program, but I would probably give them a more clear message saying, for example, saying, you know, I found a J in your DNA sequence at some position. You should really go see to that. So does that kind of make sense about how I would deal with that for Emily Towner? Okay, perfect. Yeah, so dealing with that kind of errors is the exact kind of use case for a try except block. All right, and this is not from last class anymore, but this is actually going to be the first class we write. So you should have this already coded out in, you should already have this coded out in the course materials that you downloaded. But here we have a whole class called DNA sequence, and this is just a class to handle DNA sequence itself. So going over this, we can see that there's a couple of basic things in the in building out the class. So we have our init, which again is our constructor. This is how we initialize the this is how we initialize an instance. And I'll go over these in a lot more detail in a moment. We have get %bases, so this is going to be a method. You'll probably notice I'm a big fan of giving functions fairly long names. So again, as I mentioned, in this class, I'm more focused on teaching you how to approach writing a Python program and trying to solve a problem rather than any individual aspect of the coding, although I am very glad I got to teach you guys about dictionary, because definitely not learning that would have been a big hole in your knowledge. So understanding, for example, why I give things long names, like get %bases. If I just look at this name, it tells me what it's going to do. And it's also kind of nice because it tells me what it's not going to do. So this should just get the percentage of each base and not really do a whole lot else. And this is another thing to think about when you're writing a program, is creating objects helps you keep your code organized and reusable, and coming up with function names that kind of describe the scope of the function should tell you what the function does, and it should kind of give you, and it should kind of always give you a reminder what the function doesn't do. And that helps avoid a problem I call scope creep, which is where you start piling on more and more stuff into this function until eventually this one function becomes, 200 lines long, and it becomes very difficult to kind of deal with it when there's bugs. So again, I have a function here that gets percentage basis. I have a function here that gets the GC content, or I should say a method. I have a method here that's going to count mismatches, and we'll go over how that works in a bit. So the first thing we got to do when we're building out any class is we have to declare a class and initialize it. So the class is just DNA sequence, and this is something called what it's a subclass of. So it's a subclass of object, which is just, in Python, if you're a subclass of object, you're basically the most basic object you can be. So we have our init, which is our constructor. And the only thing we really need to build out a DNA sequence object is the DNA sequence itself. So a couple things we're going to do. I don't know if people saw this upper function, but here we're saying sequence. We're starting off with sequence, and we're saying self.sequence. So we're assigning something to an attribute, and it's just going to be sequence.upper. So this will help us because we now know that our DNA sequence is going to be all uppercase. And this could be important because a lot of times people will give you DNA sequences that are lowercase, or sometimes DNA sequences that are mixed case. We're going to say self.length, and then we're just going to take the length of the DNA sequence itself that was submitted. We're assigning here an attribute called self.percentBase, and we're going to use that getPercentBase function I just mentioned. We're going to have an attribute that's the GC content, and we have a method of getting the GC content. And we're also going to initially assign a reverse complement. So we're going to actually start off just automatically determining the reverse complement for the sequence. And since reverse complement is actually a function that exists outside of this class, we call it from outside, and we just pass it self.sequence. So the nice thing about having done this is we have an idea for the first methods we need to write because we know what methods we're going to need initially. So again, we already have our reverse complement calculator. I showed you that. And now we know what methods we're going to need. So we're going to need a getPercentBases method. Can anybody tell me what I'm doing here on line 25, the first line of this method? Yeah, I'm initializing an empty dictionary. And just like I did already in the last example, and like I'm probably going to do, like I said, about 50 more times in this class, I initialize an empty value, and then I kick off a loop to iteratively add to the thing I initialized. So here I'm doing for base and self.sequence, so I'm just iterating over the sequence again. So here I'm saying if not base in collection. And this is kind of a really handy tool when you're dealing with dictionaries, because as I mentioned, if you try and look up or do something to a dictionary for a value that's not already in there, for a key that's already in there, you're actually going to get a program crash. So here what I'm saying is if the base is not in the collection, so this is my collection, and if I check if something is in a dictionary, it's going to check and see if it's in its list of keys. So if I haven't seen that base yet, then it's going to initialize, and this is actually another initialization, it'll initialize collection for that base to 0. And regardless of whether or not it had to do that this round, it's then going to do this collection of that base plus equals 1. So when you see something plus equals 1, that basically means it's an integer that I'm using as a counter. And plus equals 1 is essentially saying to increment it by 1. So it's just keeping a running count of each base as it goes through the sequence. Once it's done going through the entire sequence, it's going to say now for each base in the collection. So now it's going to iterate over the bases that are in the dictionary. And it's going to change that value. So it's going to say collection of that base is equal to, is equal to the number of times I saw it divided by the length of the sequence, which gives me the percentage of each base, and it'll just return that dictionary. So that I think should make sense to people. And again, I'm going to give people a little bit of time to play around with the code here and try out different things. A couple more methods. So get GC content. And the nice thing with this is, since I know that we just calculated percentage bases, the GC content is very easy to figure out once you've calculated the percentage of each base, because it's just the percentage G plus the percentage C. So it's going to go through the that percent base, and it's going to look for G. And if G's in there, then it's going to say total percent plus equals percentage base of G. Then it'll do the same thing for C. It'll add in the percentage of C. Also, it'll do, if it doesn't find the base there, it'll do total percent plus equals 0. So what you probably noticed up here is, just like so many other times, I'm initializing an empty integer, which an empty integer is essentially initializing an integer to 0. So I'm initializing an empty integer, and then I'm just incrementing it every time. I'm incrementing it or adding to it for the percentage of each base. Here, this line isn't totally necessary, but it's saying that if a base wasn't even in the sequence, then just add 0 to the total count, or to the percentage count, and then it's going to return the total percent. I also have a count mismatches function, or count mismatches method, and this one needs another sequence. I want to introduce something called the assert statement. So this is another way of dealing with people handing me weird stuff. And here I'm saying assert the type of the other sequence is a string. And so if the other sequence is something that is not a string, then it's going to throw an error saying, it's going to actually crash out the program saying that the assertion was not met. And also in this case, I'm only comparing sequences of the same length. So it's saying if the length of the sequence in this object is not the same as the length of the sequence that's applied, throw another error. It's also going to make the other sequence uppercase, since I said that we're dealing with DNA sequences only in uppercase. Mismatches equals 0. So anybody know what I'm doing here? Where I see mismatches equals 0. Yeah, I'm initializing a variable, or in this case specifically, I'm initializing an empty integer or a 0 integer. Typically, when I'm initializing an empty integer, I'm essentially initializing some kind of a counter or some kind of an accumulator. So it's going to go through. It's going to go through the sequence, or it's going to, in this case, it's going to build out a list of numbers that is the range of the length of the sequence. So if I have a 5-base sequence, it'll go 0, 1, 2, 3, 4. And it's just saying if the sequence of this object at a given position is not equal to the base at the sequence that was supplied for comparison at the same index, then increase the mismatch count by 1, and it'll return the number of mismatches. So I just basically built a mismatch counter. And then the last thing I did, you'll pretty much always find me overloading string in most of my classes, because that weird looking thing where it just gives a description of, where it just gives the name of the object and where in memory it is, tends to be kind of useless to me. So a lot of times I can figure out something better to give. So in this case, if I try and call a DNA sequence object as a string, it's just going to return the DNA sequence itself. And then finally, some test code. So I put test code behind the statement of if dunder name equals, and then in quotes, dunder main. Do this thing. And the reason I do this is name is actually what this entire package of code is executing under. So if it's executing under main, that means that I called it directly. but it may be executing under some other name because it was called as a package. So it's saying if I import this as a Python package so that I have access to its functionality, don't run this. But if I call this as the main program, do run this. And this will frequently be things like test code. So all it's doing for test code is it's starting off with it's just building a DNA sequence object, and it's testing the overload as well as printing out all the different, calling this dunder dict value is just having it print out all of its attributes and what they come out to. And when you run it, you should see something like this. If you're using Mac or Linux, you may in your command prompt want to type Python 3 instead of just Python. In Windows, it's just going to be Python. And so at this point, yeah. So at this point, I'm going to leave everybody a chance to run this and start messing with the code. So for let's see. So I have a question from Mo Ishihara. For the init section, when do you use self.something versus sequence.something? So let's go back to the initializer. So if you notice up here, I never actually use sequence.anything. Or no, I take that back. I think, yeah, I do sequence.upper. So sequence.upper, this sequence is an instance of the string class. So having this string convert itself to being all uppercase, that's a method that's built into this string. So in this case, because it's built into the string, I'm calling sequence.upper. Self is referring to stuff that relates to this DNA sequence class object that I'm building. Does that answer your question, Mo? So we can't call self.upper because this has there is actually no upper function in sequence. So keep in mind that, for example, in this DNA sequence class, the DNA sequence itself is just a string of A's, T's, G's, and C's. So it's a text string or a character string. But length, that's going to be an integer. And it wouldn't make sense to have an integer.upper function, right? Actually, let's do this. Actually, Mo, you don't have a microphone if I remember from last class, right?
I have a microphone.
Oh, okay.
Yeah.
Cool. So everybody can hear? Okay, awesome. Okay, so let's try going over this now. We can be a little bit more interactive here. So for self, so all these selves are referring to the DNA sequence object. Sequence.upper, this is a completely different value that's just being contained within the DNA sequence object. Does that make sense?
So sequence is already built in the class because we haven't defined sequence here. We just
I'll show you where the sequence gets defined. So that's actually there it is. So here I'm saying test equals DNA sequence, and I'm passing it just this A's, T's, G's, and C's here. So this value right here, the set of A's, T's, G's, and C's, comes in right here. It comes in as sequence.
Okay.
So I'm actually calling upper on that.
Okay, and the self is just the variable in the class.
Yeah, it's a method, or it's a method, or it's an attribute of the class. So for example, So for example, here, if I called DNA sequence.sequence, it would return to me this ATG, ATGC, 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 all uppercase.
Okay.
But as you can imagine, for strings that have, they have the method upper to make them all uppercase. They also have a method called lower that'll make them all lowercase. So if I call DNA sequence.lower, it'll give me an error because I don't have a lower method described for DNA sequence. But if I called DNA sequence.sequence, which refers to this, .lower, that would actually work, and that would return ATGC, 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 all lowercase.
Okay. Do we have to, so in here, we don't have to say test equals to DNA sequence self and sequence. We don't have to write self when.
Right. So when you call things in objects, the self, you don't have to pass self in the arguments, except when you're defining the the methods themselves.
Okay, so in this case, if we write self, it doesn't work.
Right. Putting self here wouldn't do anything because self is actually undefined outside of the DNA sequence object.
Mm-hmm.
So self is usually going to be the first argument, but it's actually passed silently in there.
Okay. So back to the initializer. So we're writing self.sequence equals to sequence.upper because self here is not any type, and only like sequence is the string type that we can call upper function. And same
sort
thing.
of. So self is actually a type, and the type for self in this case is DNA sequence. It's this.
Okay. I see. So class.
Yeah.
Okay.
The type is actually the name of the class.
Okay. All right. I think I understand now. Thank you.
Okay, perfect. All right, so I'm going to give people, let's see, yeah, it's 3:23, so it's been about an hour since our last break. So yeah, we're now going to have a lot more break periods for people to mess with code. So mess around with this, change things, have it print at different points so you can see what it's doing. And basically feel free to mess around with it a little bit. And we'll pick up again, I think for this, take about 10 minutes. So we'll pick up again at about 3:35. And of course, everybody's welcome to use this opportunity for stretching, restroom breaks, getting food or drink or whatever else you may want. If you have questions or if something's not working, feel free to put it in the chat window. And we'll get to it when I get back here. And I'll see everybody in a minute. I'll see everybody in about 10 minutes.
Hey, Michael, it's Eloy.
Hey, what's up?
After class, is it cool if I call you? I gotta follow. I gotta uh, update you on a few things. Okay. All
Yeah, sure. Yeah, just give me a call when class is over.
right. Cool. Thank you.
Hmm. So I have a question, it looks like, from Caitlin Amalt, asking why when... Okay, yes, you have to change it in the circled part. It's actually not taking command line arguments. So yeah, number one, if you didn't save the new file, then you would need to save it so that it does that. But assuming that you did save, you can't just pass it a sequence on the command line. It's not actually programmed to read from the command line. All right, so I think we can pick this up again. So did anybody get anything interesting out of, anything unusual or unexpected out of this? Or was anybody encountering any difficulties? All right, I don't see many comments showing up, so I'm gonna figure probably not. So again, when we run it, it just prints the, it prints out the DNA sequence. And we also see all the different attributes that were set up. So we have sequence, and it's that, of length 12, different percentages of each base. So in this case, we have even percentages of everything. It's 50% GC content because we have even percentages of everything. And we have the reverse complement as well. Okay, so now the question is, now what? So if your testing worked and everything made sense, you're gonna save this. So you should already have this available in your collection of code. So now we can get back to our main question, which is, how are we going to attack the SAM file? Because really our first challenge is just get somebody that can read a SAM file and make it into easily parsable data. So we know the SAM file is a collection of SAM data lines. So if I wanted to store a collection of SAM data lines, everybody just punch into the group chat, what do you think would be the best data structure for storing a bunch of SAM data lines? We know we're going to make a kind of a custom object or a custom class for handling SAM data line, but do we need to build a custom class for handling the collection of SAM data lines, or does anybody think that there's maybe one that exists that does just about everything we need? All right, I have a suggestion of list. I have a suggestion. I have two suggestions of dictionary. Now another list. Now somebody's saying a tuple or a list. All right, so I'll start off with tuple because that's an interesting one that I don't really see often. Tuples and lists are actually very similar in Python, but they have a key difference. Tuple, you can't add or remove stuff. So tuples are what are called immutable. So with a list, I can say list.append, and I can add an element to a list. Tuple, I can't append something to, and I can't really change a lot of values in a tuple. So that's why you always see me initializing, that's why you'll see me a lot of times initializing empty lists, but you'll pretty much never see me initializing an empty tuple, is I can't add to a tuple. So as far as a dictionary goes, especially from the, from it looks like Kathy Lawrence and Mo Ishihara who suggested dictionary, one of the first questions you should ask if you think this would probably go well in the dictionary is, what would be my key and what would be my values? So I'd like to hear from you guys. What's your suggestion for key and values? Okay, so you're suggesting a shorthand name for the line as a key and the value as basically the object containing the line contents. That's not a terrible idea, especially if I wanted to be able to look things up quickly. And in fact, we actually kind of have something that would already function reasonably well as a key. There we go. So the same line read ID up here, this is actually going to be unique for each read, with the exception of a forward and a reverse read. So sometimes, so you can read a DNA strain in both directions. So a forward and reverse read will have the same read ID, but opposite directions. So in theory, if I do the same read dot, if I do this number dot 1 or dot 2 for the read direction, yeah, that would actually make a pretty good key. So that would be a good way of making this into a dictionary. And depending on my expected use case, that would actually be a very valid way of storing these. On the other hand, if I just wanted to iterate over all the lines in the SAM file, which is actually what I'm planning on doing here, then it turns out that probably the best way to store it is going to be a list. So because we're not going to try and look things up by, because we're not going to be trying to look things up by read ID, we're actually going to use a list so that we can just kind of append to it at will. So yeah, and again, people who said, so again, for the answers I got some suggestions of lists, some suggestion of dictionary, and one who was sort of between tuple and list. So I think the only one here that I would say is objectively not a good solution is probably tuple, just because of some properties of the tuple, which I suspect you weren't completely aware of. And then after that, the question just becomes, what's my use case? So because I know that my use case is going to be just doing a lot of iteration over all the different lines without necessarily having to rapidly look up lines by name, dictionary is probably not the optimal. The optimal is probably list, because going through a list tends to be computationally very fast. But I like the answers that I was given, and I like the explanations I was given for why a dictionary would be a good way of storing this. And if my planned use case was actually just a little bit different, dictionary might have actually been the right choice. But since you didn't know what the plan was, and in fact, it could be entirely valid that in the future I would have wanted to put in dictionary because maybe I wanted to extend the use. Again, not really, there's some good answers here, and to really become a programmer requires thinking about what's my intended use case and what's the best data structure for my intended use case. And I'm seeing a few people who are already doing that, which is kind of the goal of this course. And if you'll excuse me for just 1 second, I have a message I need to check on. Sweet. Okay, I apologize again if I occasionally have messages I have to respond to during class. As I as I mentioned earlier on, I'm currently working on a SARS-CoV-2 detection system. Where basically, if anybody out there does quantitative PCR, especially if you're working in a lab that does quantitative PCR for detecting pathogens, which is a really common way of detecting SARS-CoV-2 right now in clinical and research settings. I'm developing bioinformatic methods to basically improve how that works and to automatically analyze curves and detect possible false positives or curves that need detection. How I do this, depending on where I am with the program, might be something I actually cover on the third day of class, because my third day is kind of open. But because this is something being actively developed, I occasionally get phone calls that I have to answer because people are actively working on SARS testing with it. So I apologize if I occasionally have to take questions like that, but obviously this is not, judging by the fact that we're all sitting here remote and nobody is on campus probably, these are not exactly normal times. Okay, so going back to how we attack the SAM file. If we want to figure out how to attack the SAM file, the first thing we probably want to do is we probably want to just look in at the SAM file and see what it looks like. So looking at the SAM file, we see that it's what's called tabular data. It's basically data that is set up in a two-dimensional, it's basically a two-dimensional table. So each line contains one full set of data. And in between each piece of data on each line, we have what appears to be a tab. We can also look at it and tell what stuff is. So we can tell, for example, that read name is the first thing. We can tell that the flag score is next, chromosome and all that stuff that I showed you before. We have this quality string, which again, we're not going to worry too much about what it is for the moment, but we'll do something with it a little bit later. We also see up here that we have a couple lines that aren't exactly like the others. So these lines start with the @ symbol, and we have one that's called SQ, and it says something about, we're guessing, chromosome 14. All right, somebody's having trouble with the video, although yeah, it looks like only one person is having it. Yeah, the screen should not be black on your end. You should be seeing my PowerPoint slides. So anyway, we see that there's a couple of these lines that are called, I typically just call them SAM file headers. The nice thing is if we look at them, we realize really quickly they all start with the @ symbol. So here I have a little bit of code that I'm just writing in the Python shell. And I'm telling it to open up a file. So I'm telling it to open up the sample SAM data file. I'm telling it to read a line. I'm telling it to split the line. And when I realize, oh, that first line is actually header data that I don't want, so I'm going to tell it to skip a line, and I'm going to tell it to read another line. I'm going to split that one on tab, and then I realize, yes, it splits everything up quite nicely. Although one thing that's kind of interesting is these tags form their own fields, so I have a bunch of fields out here I don't want. The other thing is I need to have a way of getting rid of these lines that start with the @ symbol. The other thing, and this one's a little bit more subtle, is who knows what this \n means? Yep, new line. So \n means new line. Do I want that new line to go in with the data? Yeah, that's pretty much a universal no. In fact, getting new lines mixed in with your data typically can screw you up really badly. So does anybody know the Python function to get rid of those new lines? Yes, looks like Biden Win said it, strip. So you remember how I said that in Python, everything just about is an object? So in Python, strings are actually objects. And the nice thing about strings being objects is they can have a bunch of methods attached to them. So for example, we've already seen methods attached to the string object. to convert everything to uppercase letters or lowercase letters. And another method that people have seen a lot in string is strip. And the function of strip is to take non-printing characters off the beginning and end of the string. So in this case, because the \n or the new line character is a non-printing character, strip will get rid of that, and it'll get rid of any other garbage on there. Also, this thing has the most hashtags. So iterating over a SAM file, we know that we're going to have some function that reads SAM line, so we're going to define a function. Here you see me defining and initializing an empty list. After that, we have SAM file, and here I'm just saying open a file. So I'm opening the file name, which in this case is passed into the function. Line equals samfile.readLine, so I'm just reading a line from the file. So I'm initializing this to the first line of the file. Now I have a while loop going. So while there's something in the line value, the first thing it's going to do is it's going to strip away, it's going to run strip on the line, so it'll get rid of that \n. If I strip the line and there's nothing left, so the line was entirely non-printing characters, which means somebody put in an empty line for some reason, it's going to continue, or well, first it's going to read another line from the SAM file, then it's going to continue, which just is going to send it back up here to rerun the process. Assuming there's something left after I strip the line, it'll then perform this check where it's saying if the line starts with the @ symbol, then read the next line and continue, because those lines that start with the @ symbol are headers and we don't care about them right now. So it'll go back up here. But assuming there is something on the line besides non-printing characters, and assuming the line doesn't start with the @ symbol, the next thing it's going to do is it's going to append onto this line collection a SAM line object containing the line. It's going to read the next line from the file just as before and go back up to the beginning. And then samfile.close, so it's just going to close down the file, and it'll print out a message saying how many lines it read, and it'll return the collection of lines. So does anybody know what this SAM line object does? All right, I'm seeing mostly silence on the chat, which is good because we don't know what the SAM line object does yet. Well, we know roughly what it does. We know that it's an object that contains data from each line in a SAM file. But how we do that, we don't know yet. What's cool though is we know that we're going to have the SAM line file just take in a raw line of SAM data. Okay, and somebody's saying file handle. No, so file handle is actually what most people would refer to a file handle is actually SAM file up here. So file handle is basically the object that handles reading and writing files. So SAM file is a file handle that contains the SAM data, that contains the raw SAM file. So SAM line is the class that is going to actually handle our SAM data. And that's not going to be a file, that's going to be all in the computer's memory. So again, we don't know exactly how we're doing this, but we've defined it here and we know we're going to need one. So we know we're going to need a SAM line object, and we know the SAM line object is going to take basically a raw line of SAM data. It's actually kind of cool when you think about it, because while we kind of already know the basic function of iterating over a file and skipping lines that start with a certain symbol. And as we did that, we realized, oh, well, the thing we're going to need is actually here, something to handle SAM lines. Again, this is kind of approaching how you actually get down and write a program when you have to. So we have class SAM line, which is the thing that we realize we're going to need. We have an initializer. We also have, again, our overloaded string, which is just going to print out the raw SAM line. And what we're taking in as an argument, so remember, self is sort of handled automatically. We don't have to pass that. We just have to pass it the raw line of SAM data. we're also going to import the DNA sequence handler. And this is actually where you start seeing some of the power of object-oriented programming. Since we have our DNA sequence handler built and working, and we know how to interact with it, we're just going to import DNA sequence handler. And that gives us access to all of the work we've already done. We don't have to copy paste anything in here and make this incredibly long. So the first thing is we're going to do self.rawline equals rawline.strip. So that's just basically going to store the raw SAM line. We're also going to have a line array, and this is calling the split function on the raw line, splitting it by the tab character. And then I'm setting a bunch of different attributes. So it's just setting self.readID equals line array of element 0, self.flag equals line array element 1, stored as an integer because we know that the flag values are always integers. Self.chromosome equals line array element 2, self.read position, line element array 3, stored as an integer because again, these values are always integers. Friend scores, integers, cigar strings, those are strings, and so on and so on. Here we're saying that if the mate chromosome is the equal sign, then the mate chromosome is actually just self.chromosome because the equal sign means it's the same thing. So this looks like a long line of basically repetitive code, and essentially it is. All I'm doing is I'm taking that SAM line and I'm assigning a bunch of different attributes of this object based on those things, just going in order from 0 all the way down to the 11th element, which is index number 10. And then I have this thing called other values, which is going to be 11 and on, and that's going to correspond to these guys over here, which we're not going to worry about for this class. But essentially what we're seeing here is just that these are a bunch of values that we may still want to store because maybe we'll need them later. So we now have our SAM line object. And we've basically created that thing that we just said we need. So we'll also throw in a little bit of test code, and we'll throw this in at the bottom, saying, again, that thing to say, if we're calling this directly, then SAM lines equals read SAM file lines, and we're calling and we're going to open up the file sampledata.sam. And for I in range 10, so basically for numbers 0 through 9, we're just going to print the SAM line at each index. So since we stored it as a list, we're just going to go through the first 10 value. We're just going to go through the first 10 lines and print them out. So this will print out the raw line. And when we run it, we find out that we read about 500,000 lines. And here we see that we're just printing out the first 10 lines of the SAM file, which is kind of what we expected. I can also mess around with this in the Python shell a little bit. So you can see here that I import SAM reader, which immediately gives me all that functionality from the SAM reader that we just wrote. The SAM lines equals, and here I'm just telling the reader to read the sampledata.sam. As soon as it's done, it'll tell me how many lines it picked up. And here I'm just picking a random SAM lines value, so 424242. And for example, if I call sequence.sequence, that's going to give me back the DNA sequence. Because remember, this sequence is a DNA sequence object. So sequence.gc content here, it'll tell me how much GC content I have in that sequence, and it'll tell me the relative abundances of each base. So we have basically a working SAM file reader here. All right, so as a sort of a summary, why do we like object-oriented programming? Objects help keep your code organized. One thing you probably noticed is rather than have a really long script, I can have pieces in different files, and each file just handles one part of the program, and then I call them all together to actually run something. So I don't have to worry about debugging a 2,000-line file, which I've done before, and it friggin' sucks. Objects help keep code simple and short. So you probably noticed that a lot of my functions were really, really short. Just to go back up really quickly and show some of them. This is probably the longest function I had in all my material. And the only reason this one's long is because you see that I'm just going over value by value and assigning a bunch of attributes for the object. The ones where I'm actually doing something, like for example, my DNA sequence handler, a lot of my functions, and I'll even go up a little further so that we can see everything on the page. If you look at the lengths of a lot of my functions, this one is 6 lines. You know, basically everything here, I don't think I have a function here that's over 10 lines long. And that is actually by design. I don't like having functions that get really long. Long functions tend to be hard to debug, and they tend to be a mess when I deal with them in the program. So I kind of have a rule that I like to follow stylistically, where I tell myself that no function should ever be so big that I can't easily print it on a sheet of, that I can't easily print it 14-point font on a single piece of paper if I wanted to. My other rule is code packages. Once they start hitting about 500 lines, I start thinking about, can I break this up? Once they start hitting 1,000 lines, I think I should break this up. Once they start hitting 2,000 lines, then it basically becomes, I need a very good reason not to be breaking this up. Keeping your code nice and modular makes it very easy to maintain compatibility. It also makes it very easy to keep track of what does what. So keep your code simple and short. Keep your functions sort of short and self-contained. Keep them to a single scope. Don't have them kind of don't add on new functionality instead of just adding on new functions. Your code stays reusable because you can import it anywhere. And it keeps code accessible. So anybody out there in class use the Python requests library? Okay, I don't see anybody who's used the Python requests library. So I'm going to switch my share over really quick to show something kind of cool. Oh yeah, that's right, it won't solve the whole thing. All right, so there's a really great Python library called requests that helps you get stuff off the internet. Yeah. So it looks like a bunch of junk here, but anybody who's familiar with HTML code or JavaScript or how web pages are coded this will start making sense really quickly. So for example, you have here an image, Google, thank you doctors, nurses, and medical workers. And essentially what I pulled up here is the Google search homepage. And this is all the code behind it. So that is fundamentally what request.get does. The cool thing is I have no idea how to make a raw HTTP request in Python. I don't know how, I know how those requests kind of are transmitted. I don't know exactly how to make a raw HTTP request of a server. And the good news is I never really had to learn, because I know that if I just tell request.get to get something, then request.get will basically get it for me. And then I just need to know what am I getting, and how do I interact with the requests object that got it. So if you're doing something very complicated, like some kind of statistical analysis or something, and you really don't need your users to worry about how you did it, you can actually just put it into an object and they can call it up and just get back what they need without having to worry about how to do something more difficult. All right, so as far as homework goes, everybody here has code and sample data. Basically, your goal is to play around with them, maybe try and extend some functionality of them. There's a term that I've always liked, which is basically saying code fearlessly, or don't be afraid to fail. Trying to program something that you don't know how to code is actually how you get better. So with that, I will take any questions anybody might have, and I'll stick around for a few minutes to answer them. And I'll basically I'll stick around here until I don't have any more questions in the chat session. Otherwise, everybody is free to go on, and I will see everyone tomorrow after lunch. Okay, and I have a few questions. I have a question coming in, probably a few people wondering, is there anything that you have to turn in for credit? And I believe that Eloy is just monitoring the attendance. So I don't think anybody has to turn anything for credit, but the one to check with regarding issues of course credit would actually be Eloy, not me.
Hi, Michael. I have a question.
Oh, go for it.
So for the DNA sequence handler, the reverse complement sequence was not defined in the class itself. It was like above the DNA sequence class. It's the slide 38 if you want to see it. So is it okay to use function it's not within the class as
Yes.
long as it has access by either importing or on the same file?
Yes, as long as it has some way of knowing what the function is that it needs to do. So as long as it knows, so for example, in the case of the DNA sequence class accessing the reverse complement function, the reverse complement function is in the DNA sequence package of code. So it knows exactly where to find it. It's in the same package.
Okay, thank you.
Yeah, otherwise you'd have to specify and basically tell it, you'd have to probably import something and tell it where to look to get that package of code.
Okay, so for the import, if you have the same, if you have the file that you want to import in the same directory, then you don't have to specify location. Yes. Okay, just the file name. But if it's not, then have to say
yeah, if it's in a different directory, that can be a little bit tricky. And you generally want to have it in a directory somewhere under the current directory, because trying to go up levels, Python tends to get upset at you for that.
Okay, got it. Thank you.
Yep, of course. All right, I have a question from Naomi Barber Choi asking, could I use a context manager to open the file, like a statement like with open file name as SAM file? Yes, and I think actually for a lot of people, that's their preferred method of doing it. I wouldn't be surprised to find out that somewhere there's a Python standard that you're supposed to specifically do it that way or whatever. I'm not big into enforcing a ton of standards on people. There's a few things that I like that keep your code readable and make it more functional or better handling errors. But yeah, in my case, I tend not to be a big user of the with context manager, but it's definitely perfectly valid. And if that's something that you're used to doing, feel free to do it. That is definitely a completely valid way of doing it. I just, yeah, I tend to open files and close files the same way that I did when I was programming in Perl, and Perl didn't really have context manager like that. As far as the video link goes, I think that'll probably be emailed out. That's going to depend on Eli, I think, but yeah, I'm sure that can go out. Shuki Wang is saying, I normally use seek.io from BioPython to read fastest sequences, but never use it for SAM files. So yeah, seek.io is also a very good library. I personally have my own FASTQ reader I wrote because I actually wanted some functionality in there that I wasn't getting out of seek.io. Also, seek.io has a lot of stuff in it that I never use, so I was like, why do I want that kind of unnecessary heaviness? But yeah, it all depends on personal preferences. Seek.io is also a perfectly valid package in BioPython. BioPython's very good, although a lot of times I tend to just try and roll my own stuff unless it's something I really don't want to do. And actually, personally, I like to roll my own stuff also because it's a good way to get very familiar with the file format. It's a good way to really understand the data that lives in the file and how it's structured. And it also tends to make you kind of a more seasoned programmer of just figuring out how to write these things. But there's also advantages to not reinventing the wheel. Okay, so Mo has a question from this morning. What do the negative values in Selexa mean? So Selexa's scoring scheme is not actually a true Phred score. So Phred score has its own formula. The Selexa scoring scheme at the high end, so around like 30 and 40, a Selexa score of 30 or 40 is about equivalent to a Phred score of 30 or 40. At the very low end, they tend to be fairly different. I don't go into detail on teaching the difference between the two because, quite frankly, nobody ever calculates either of those scoring schemes in their head. And Selexa's scoring scheme, actually, even dealing with it by the basic rule of thumb I gave, is a pain in the butt because at the low end, it doesn't follow that rule of thumb. So Selexa's score can actually go negative. And I think a -5 on Selexa is roughly equivalent to 0% confidence. But yeah, just in the interest of time, I didn't really go into how those are into the Selexa scoring equation because the Selexa scoring equation is a pain in the butt. And nobody ever uses it anymore. All right, so I think I don't see any more questions, so I will see everybody tomorrow.